In this video, I will show you a simple demonstration of neural network on a simple logic problem, as well as the basic mathematical ideas behind it. Also, we will design our basic problem on Jupyter Notebook or NumPy. First, let me show you a basic XOR gate. A basic XOR gate has two inputs and one output. The XOR gate only outputs a value of 1 when only one of the inputs has a value of 1 and the other is 0. Creating a sample data plot of an XOR gate would result to a plot that would really be hard to be solved by linear regression. One approach that we could use in this problem is by artificial neural networks. Given this problem, we will have two input neurons on the input layer, four hidden neurons on a single hidden layer. Now I say single because we have to remember that the hidden layer can have multiple layers, and one output neuron on the output layer. Now synapses are the links that connects every other neuron in the network. The basic function of a synapse is to take a value from the input, multiply it by specific weight, and outputs the result. These results are then sent to another neuron where the outputs from all the synapses are added together. Once the outputs are added together and an activation function is applied, in this case we are going to use the sigmoid function. In this example, it is important to note that scaling of the input values are not done because our input values have the same unit. In cases where the inputs are of different units, it is important that we scale them first before entering them to our neural network. Now from this neural network model, we can derive four formulas from it. These formulas are represented in a matrix notation so as to make our analysis simpler and easier. First is the Z2. Z2 is equivalent to the matrix product of the input matrix, which is denoted as capital X, and the W1 matrix, which is the weight of the first layer of synapse. Second is A2, which is just the application of our activation function on the second layer, which is in this case is the hidden layer, and we can simply denote it as a function of Z2. Third is Z3, which is the matrix product of A2 and W2, and lastly, Y hat, which is Z3 applied with the activation function. Now, later on in this video, we would see that on our first set of approximation, the approximates are far from the expected output. We use the cost function j to express exactly how wrong or how costly our model is. The cost is just a summation of the squared error values. To make it simpler, we could just represent this as the summation of half the error values. Now our goal is to make j as small as possible, so as to make our approximation as close as possible to our expected output. We could do this by doing a method called gradient descent, where we observe the rate of change in j with respect to w, or simply the derivative of j with respect to w. But since we are just observing one weight at a time, it would be the partial derivative of j with respect to w. In the value of our dj dw, or the partial derivative of j with respect to w is positive, then we are going uphill. If it is negative, then we are going downhill, which is exactly what we want. Determining where is uphill or downhill is the core of gradient descent, and the key part on how every sophisticated algorithm are trained. Now, we do this moving continually and stopping when the cost stops getting smaller. But there's a problem with this method. This method is ideal for convex function that has only one local minima, but when it is applied on non-convex functions, using this function could lead us to just the local minima of the function, and not the global minima. Now, the solution is by using a stochastic gradient descent, which uses individual examples in finding the global minima of the function, or the correct value for our cost function. But it won't be further discussed in this video. We will just focus on batch gradient descent in our example. In order to perform gradient descent, we will need equations, code, and the partial derivative of j with respect to w. The code part will be shown on the latter part of this video. Now our weight is divided into two parts, namely w1 and w2, and so we perform partial derivative of j separately on both w1 and w2. It is important to note that our gradient values matrix must have the same size with our weight values matrix. By substituting our actual cost function to the equation and performing partial derivative, we are able to get the partial derivative of j with respect to w2 is just equivalent to the negative of the difference of y and y hat multiplied by the prime sigmoid of z3 times the partial derivative of z3 with respect to w2, where the negative difference of y and y hat multiplied by the prime sigmoid of z3 can simply be denoted as delta 3, which is the backpropagating error. Backpropagating is the backpropagating of errors to each weight. The partial derivative of Z3 with respect to W2, on the other hand, is the activity of each synapse. It represents the change of Z on the second layer with respect to the weight on the second layer. Doing the same calculations on W1 gives us the partial derivative of J with respect to W1 is equivalent to delta 3 multiplied by the transpose of W2 and multiplied by the prime sigmoid of Z2 times the transpose of X, where the transpose of W2 is just equivalent to the partial derivative of Z3 with respect to A1, and the prime sigmoid of Z2 is equivalent to the partial derivative of A2 with respect to Z2, and the transpose of X is just equivalent to the partial derivative of X2 with respect to W1, and the product of delta 3, the transpose of W2, and the prime sigmoid of Z2 is equivalent to delta 2. With those formula, we can now compute for our dJdW, or the partial derivative of J with respect to W, whereas adding or subtracting a scalar value will determine which direction is uphill or downhill, which will be shown in our implementation on Jupyter Notebook. Now, to train our model, we will have to use a mathematical optimization algorithm called BFGS, which overcomes some of the limitations of our plane gradient descent and allows us to find solution more often and more quickly. Once trained, we just replace our random parameters with our trained parameters and see how our trained parameters compares with our expected output. Now, I've run these codes prior to this video, so as not to make this video lengthy, but I will discuss some important parts in this implementation. Now, we could see on out block number 3 and 4 on our Jupyter Notebook our X matrix, which shows our input matrix, and our Y matrix, which represents our expected output matrix. Now, in our initial class neural network in block number 6, we define our hyperparameters, which are the input layer size, output layer size, and the hidden layer size. We set our parameters first to random since we don't have our trained parameters yet. And we also define our sigmoid activation function. We see on out block number 9 that the approximation of our model is far from accurate as compared to our expected output, shown in out block number 10. In block 11, we redefined our neural class and added the definition of our cost function and the prime of our sigmoid and cost function. Out block 15 and 16 shows the value of our djw1 and djw2, which is just our partial derivatives of j with respect to w1 and w2. Now we add and subtract a scalar value to observe which direction is downhill. We could see that by subtracting, our cost starts to decline as compared to adding. We again redefine our neural network class in order for us to continue with our next steps, which includes our numerical gradient checking. With this, we will be able to check whether our computation and our code is in agreement with each other. Out block number 26 shows a pretty good value that indicates that we have our code and computations correctly. Now we train our model using a mathematical optimization algorithm called BFGS. As we could see on the plot in out block 32, it would take around 49 iterations in order for our model to find the least value of our cost function. And now we compare our trained approximation results for our expected output. We see that our model is highly accurate in approximating our expected value, with the first and last values having a value that is very near to 0, and the second and third values which has a value of exactly 1 and very close to 1 respectively. That's all for our sample toy problem and artificial neural network implementation. Thank you for watching.